All right, hello everyone. Is it one? It is one.
How's it going?
It's going. I've been staring at my computer all day, so I'm like done looking at a computer. But I have a lot of deadlines this week. So, anyways, so I wanted to start off today. One of the advantages to having two classes, I have two Cal 2s. One of the advantages is that I get to go through the material a second time. And I did the lecture yesterday for my Monday, Wednesday class over the shells method and all that stuff from last time. And I think it went so much better than it did for for this class. So I just wanted to provide a link to that video in the chat if you're interested. If you want to, you can go look at that video. I just sent it. I just think it went better. I kind of approached it a different way because I felt like it was a little bumpy for us. So if you go and look at that, I mean, it'll look similar. It's just the order I did things, I think made it flow a little better. So anyways, it's there in the chat. Other than that, I want to pick up where we left off. And we were trying to finish up 7.2. And we were talking about the last part of the section, which has to do with volumes of solids using cross sections. So I'm going to bring up the problem that we were looking at. And this is the problem the way it would be presented to you, in a test. No pictures or anything, just says, base of a solid is the region bounded by the first arc of the sine curve in quadrant one and in quadrant one and the x-axis. Cross sections of this solid perpendicular to the x-axis form equilateral triangles. So we went through this. I did my best to try and explain what was going on. I thought we would, I don't know, we set up the integral. So I think what we should do is just start a new problem. And I'm going to just change it. I'm going to change it up a little bit here. Let's say we have a solid has as its base the region bounded by just going to write these in here. Y equals 1 minus x squared. And keep it simple, y equals x squared. Cross sections of this solid, which are perpendicular to the x-axis, form semicircles with the base being the diameter. Find the volume of this solid. Okay, so a lot of this is just going to be trying to interpret what the hell, this is all saying. So let's start out by just drawing the region. So we have some solid, right? The base of that solid, where it touches the ground, is the region bounded by these two curves. So we're going to just draw those two curves first. So we'll start with, I'll start with the y equals x squared. That's this parabola. And then the other one, 1 minus x squared, is the parabola that opens down like this. And the region, I think, is obvious. We've actually looked at a region like this before, so there's a region. So that's what the bottom of our solid looks like. But then it says that if we take a cross section, which is perpendicular to the x-axis, so if we come in here with a knife and we were to cut through this So the solid, we have to imagine that there's a solid above this region. We can't really tell what it looks like, but if we were to cut through that solid, what we would get is a semicircle. And that semicircle would have as its diameter the base of the actual solid. So we have to somehow wrap our heads around what that's saying. So I think a three-dimensional picture is where to go next. So I told you about this. If you draw three-dimensional, you try and draw out like a squashed down X. I mean, sorry, yeah, a squashed down X, and you kind of get that three-dimensional feel to it. Now, this is the challenging part, drawing things in three-dimensional space. So I'm going to try and draw the red curve. So I know the red curve touches, oh, by the way, this is the X-axis, this is the Y-axis. And then normally the one that's pointed up is called the Z-axis. That's not important to us. The X and the Y are most important. So if I plot, let's say, a couple of points, that red curve hits the Y-axis, hits the X-axis in a couple of spots. So what I try and do is draw my parabola best I possibly can. That's not bad, huh? Pretty good. And then I draw the blue one, and the blue one will kind of do this and do something like that. Okay, so when we take that slice, right, when we come in with that knife, and that knife is perpendicular to the X-axis, when we make that cut, I want you to imagine that what we're actually doing is we're taking a cut that has a little bit of a thickness to it. Kind of like we had rectangles before. That's exactly what we're doing. We're looking at, I'm going to zoom in on this a little bit. See, this cut is going to be like a small little rectangle, a little sliver that we're going to create from this solid. And that's the thing that we're going to be looking at over here. So it's like there's a little rectangle on the ground like this. And what we're told is that this solid form, the form, when we cut it, what we get is a semicircle, which is a half circle, where the diameter of the circle is actually the base, the length of that base. So you have to visualize that there's a little semicircle that comes up here. It's got a little thickness to it. You've got this little, I don't know.
Taco shape,
A what?
like a taco shape.
Like a taco shell. It's got a little thickness to it. Exactly. Making me hungry. Now, it's important for us to see that the size of that taco will depend on where we cut, right? So if we were to actually cut this thing, let's say, further towards the Y-axis and make our cut over here, so if our little rectangle is over here closer to the Y-axis, then in our picture, it's hard to draw because the other taco's in the way. Our rectangle's over here, and we get a bigger taco. I like the taco idea. It's a crispy taco, though. It's not soft. Okay? Don't mess that up. So the size of this slice, the volume of each of those slices depends on where that rectangle is, right? Depends on where the rectangle is. So we're going to be doing exactly what we were doing before. We want our rectangles or our slices to start at the left end and move their way across, right? Which means we're going to be integrating, right? We're going to be integrating from whatever this intersection point is to whatever this intersection point is. We'll move those rectangles across. But the thing that we're going to be adding up is the volume of one of those, right? So what we need to do is come up with a formula that would give us the volume of one of these slices. So what I like to do is I like to just take one of these slices and just take a look at it. Okay, so here's my slice. Not a great picture. I've been doing this forever and it's still somewhat challenging to draw this. Okay, so there's one of my slices. I want to know if we can come up with a formula for the volume of one of them. And then all we have to do is use the integral to add them up, right? So the
What
volume,
about using semicircles?
pardon me?
Using semicircles.
It's a
Because
half.
the top-
I'm not sure if there's a question with that.
So my question is, can we use the semicircle since like it resembles taco?
Yes, I'm still not sure. Are you saying the formula for the volume?
Yes.
Well, we don't really have a formula for the volume of a semicircle. We have, I mean, there's probably one you could look up, but all we have to do is use this principle that we've been using, which is, if you go back to the cylinder, remember the cylinder? The volume of the cylinder is pi r squared times the height. So if you have the height here, the pi r squared is the area of that piece right there, right? So anytime you want to find the volume of something, if you can find the area of one of its surfaces, then all you have to do is multiply by how deep it is, and that'll give you the volume. So
Okay. Yes.
what we're going to do here is just try and figure out first, can we find a formula for that area? Okay. And then we will multiply it by how deep or how thick this thing is. But we know the thickness, right? Because the thickness is coming from the thickness of the rectangle or the slice. And that has always just been dx for us, right?
Mm-hmm.
Okay, so we just need to know the area of a semicircle. Well, the good thing is we know what the formula for the area of a circle is, right? The area of a circle is pi r squared. We have a semicircle, so we should be taking half of this, right? Mm-hmm. So the area should be half of pi r squared. So that's what I know so far. This area should be 1/2 of pi, but now I need to know what the radius is. So the radius is the distance from the center to the edge, right? Like this?
Yes.
Which was x.
Pardon?
Which was x.
Well, is it x? Look at your slices. I'm going to put a blue dot on each of my center points. Okay? My center points.
It's R out minus R in.
R out minus, so R out minus R in, or the top one minus the bottom one, right?
Mhm.
So let me draw it over here in green. If I take that one as being the top, and this one as being the bottom, then top minus bottom gives me the total length of that rectangle, right?
Yes.
Now, I don't want the total length, I want what?
Half.
Half of it, right? I want half of it. Does that make sense? So the radius, so my radius, if I draw my radius in these rectangles on the left-hand side, I'm working over here. My radius, my center points of those rectangles are going to be halfway between, or the halfway points of each of those rectangles. So first I figure out, well, how long is the rectangle? That's top minus bottom. But then I just take half that distance. That make sense? Okay, so it'll be the top minus the bottom. That's how long it is. And then I just take half of it. So why don't we just multiply that times a half? So this right here is our radius, right? But then it's radius what?
Square.
Squared. So the whole distance from here to here is top minus bottom. That's the diameter, right? The diameter is top minus bottom, so the radius is half of that. So let me go ahead and clean this up, and let's plug things in, because we know what the top one is, right? The top one is the 1 minus x squared, the bottom one is the x squared. So the area of one of these should be 1/2.
And what was 1/2 again on the radius? What was the reason why?
Because
Right there.
yeah, top minus bottom, right? Top minus bottom would give us the diameter of the semicircle. Because it's from one edge, that's the rectangle on the bottom there. I'm highlighting that in green. That's the rectangle on the bottom. We don't want that whole distance, we want half of it. The whole distance is the diameter.
I see.
Yeah?
Mhm.
Okay. So I need to square this. So let me write down what this is. This is, let's see, the top we said was 1 minus x squared minus the bottom, which is just x squared. But then times a half, all of that times a half. This is getting messy. I have too many parentheses. And then all that squared. Let me take care of the half. I'm just going to square the half. If I square the half, it becomes a fourth. I bring it out here, it becomes 1/2 times 1/4 is 1/8 pi. And then now inside, let me just get rid of the parentheses. I get 1 minus 2x squared. All of that's still squared. So all I did was drop the parentheses and collected like terms. So that's it. That is the area of one of those semicircles. And then now I need to get the volume, I need to multiply it times the thickness, which we said was dx. So back up here to volume. Volume should be 1/8 pi, and then 1 minus 2x squared, that quantity squared times dx. That is the volume of an arbitrary semicircle little slice that we have.
And
So-
what are the limits?
Yeah, so what are the limits? Well, we want to be able to move these rectangles across the region. So we need to know where we start, right? Like, where is that and where is that? So we need the intersections. So we have to go do that to find the intersections. See, because we're about to set up the integral, right? The integral is what's going to allow us to add all these up. So we're going to set 1 minus x squared equal to x squared. And if you solve that, you should get 1 equals 2x squared. So plus or minus square root of 1/2 equals x. So here it is. Here's the final result. I want to do the integral from negative 1/√2. I went ahead and just did this, the root of the top and bottom, to positive 1/√2. Let me see, I have a 1/8 pi. I could pull that out, but I'm just going to leave it there. 1/8 pi, and then 1 minus 2x squared, that quantity squared dx. So I'm just taking that volume formula, slapping it into the integral, and that's it. That is it.
So on the exam, you would just ask for the integral, not to get the final result.
That's right. I wouldn't ask you to continue taking that the rest of the way. Remember, on the exam, I'm just going to ask you to find like the area, like all the way to an answer, like probably on the first problem where I'm asking for area between curves or something. And it'll be pretty straightforward. Like the integration won't be crazy. But I do want to make sure you can plug numbers in and do all that stuff at least one time. Okay, what do you think? Now, there is also problems where you could have your cross sections are perpendicular to the y-axis instead of the x-axis, and things change then. But I'm going to stick to everything I'm going to give you is always going to be perpendicular to the x-axis, just to kind of keep it simple. Look, the whole idea here is to understand that the integral can be used in a different manner, right, than we've been using it. We were doing the revolving around different axes and all that, but we can throw that all out and start with a completely new idea and still use the integral to be able to add up an infinite number of things, right?
Mm-hmm.
Okay. Just so we are clear on this, what if we did the same problem, but I told you that the cross sections were squares instead of semicircles? Everything would be set up the same way. I'm going to do it in orange here. All of these would be little squares instead of semicircles, right?
Mm-hmm.
And so it would look like this on the outside. Well, we know how wide it is, right? It's dx. We need to know this length and this height to get the area, but it's a square, so the base and the height are the same. Do we know how long this is on the bottom?
Top minus bottom.
That's just top minus bottom, right? There's no half of it this time because it's not a semicircle, right? So I just figure out top minus bottom. If you take the top and you subtract the bottom, you should get 1 minus 2x squared. I'll leave that to you. That's just top minus bottom. And then that's what this is, 1 minus 2x squared. And so the volume of that is going to be, well, 1 minus 2x squared times itself, right? Which means square it, and then times dx.
Mhm.
And now set up the integral. The integral would go from -1/√2 to 1/√2. Let's see, 1 minus 2x squared dx. There it is. That would be the integral for that one. That one's a little easier, isn't it? The square is a little easier than the semicircle because the formula to get the volume is a little easier. We don't have the whole like pi r squared thing, half pi r squared. And then the problem that I did at the end of class last time, oops, the one I did at the end of class last time, we did a region and then we said our cross sections were equilateral triangles. So all sides were equal. And then we had to use a special formula from pre-cal to get that area. So I would anticipate for you that if I give you a problem like this on the test, which I will, there's no question about that. The big thing for you is going to be, what do the cross sections look like? You know, and I'm pretty much going to stick to either circles or semicircles or squares or equilateral triangles. That's pretty much what I'm going to stick to. So as long as you are comfortable with those, you should be okay. All right.
My question is, so do we have questions like these in the exercise in the homework?
Two of them. There's only 2 of them. Yeah, it's numbers, I think, 38 and 39. This is
Okay,
yeah, this is in 7.2. Yeah. Now I'll give you a hint on number 39. They give you the region, and the region is an ellipse. So they give you the equation of an ellipse. And so what you have to do, as a hint here, the equation of an ellipse is very much like the equation of a circle in the sense that this is not a function of x or y. So what you're going to have to do is take the equation of the ellipse, solve for y, and you're going to get a plus or minus because you'll have to do a square root. And just remember that the plus one is the one on top and the minus one is the one on the bottom. And then you can have a top and a bottom because you'll have 2 different functions. But I want you to mess with that. I want you to see how you do with that. Okay. We're going to move on. So we're going to now talk about 7.3. Oh, sorry, 7.4. Arc length. So if you go back and you think about like everything we've done with functions in calculus so far, if you go back to Cal 1, right? We've said, okay, if we have a curve in Cal 1, the main thing in Cal 1 was we could go to some arbitrary point x, go to the function, we could find the slope of the tangent line, right? Okay, so that was, we spent a lot of time doing that, differentiation. Now we're in this class and we're realizing that if we have a curve, we can kind of start, you know, any point, any 2 points we want, we can try and calculate the area underneath that. And we can also rotate it around the x-axis, do all these different things. But one thing we have never asked is, you know, if we take a curve and let's say we start it at some point and end it at some point, A and B here, we've never said like, if I like to think about it like, might be hard to see. Usually when I'm in class, I have my belt on, so I just take my belt off. There we go. So not easy to see that, you know, but we have some curve on a flat sheet of paper, just like we have here. You know, what if you grab it at 2 points, take it off the piece of paper, pull it tight and measure how long it is, right? That would give you like the distance. If you were traveling along that curve, it would give you the distance you travel, right? That's called the arc length. So naturally you might ask, well, how in the world do you calculate the arc length of a function? So here's how we do it. What we do is we imagine zooming in on an infinitesimally small little patch of that, okay? So I'm gonna zoom in on that. So when you zoom in on that, you're gonna see some piece of curve, aren't you? Now, I'm going to take these 2 points in green. I'm gonna create a right triangle. Now we know already that this blue curve is curved. It's not necessarily a straight line, but the right triangle that I create here, that green piece, the hypotenuse, is pretty close, right? It's pretty close to the length of the blue curve. I mean, there's a lot of error there, right? I mean, it's not the same. But imagine that I zoom in even more and zoom in even more. The more zoomed in I get, the smaller that error becomes. Do y'all agree with that? The closer and closer I can zoom into the blue one, the less it's going to look like a curve and the more it's going to look like a straight line. So what's going to happen is if I can zoom in more and more and more, this blue piece, those are little arrows, this blue piece is going to start to converge to being straight. Do y'all buy that? If I'm able to like zoom in, zoom in, zoom in, zoom in. CJ, you've got this look on your face like, you're okay with that? Okay, all right. So it would be real nice if we could somehow find a formula that would give us the length, we'll call it L, the length of the hypotenuse. Because if I can find a formula for the length of the hypotenuse, then if I do an infinite number of these triangles, right, an infinite number within this curve, if I cut it up into an infinite number of little triangles and measure the hypotenuse of each one of those triangles, then as the number of triangles goes to infinity, this should converge to the true length if I add them all up. So it's the same principle. Look, it's the same thing we've been doing. We were doing rectangles, weren't we? And we were doing how many of them in here? How many rectangles were we putting in there?
Infinite.
Infinite.
Infinite number of them, right? Which meant they were getting more and more narrow, right? They're getting smaller and smaller and smaller. But it was like a limit, right? We were doing a limit, and then we were using the fundamental theorem of calculus. Same exact concept. But instead of drawing little rectangles and adding those all up, we want to draw little triangles and add up all the hypotenuses? No, all the hypotenuse. What is the plural for hypotenuse? I've never thought about that. Hypotenuse, that's a pretty cool word if that's what it is. Let's just go with hypotenuse, I like that. So we're gonna add up all the hypotenuse, an infinite number of them. But we have to have a formula for it, right? We need to have a formula for the hypotenuse. So let's just take a step back and let's remember some things. We know, let's say that this function here is y equals some function of x, right? Then when we take the derivative, right? When we take the derivative of y with respect to x, we get f prime of x, don't we? Now, if we solve for dy, we get f prime of x dx. That's just purely mechanical stuff that we've done in Cal 1, right? If y is a function of x, then if we differentiate both sides with respect to x, we get dy dx is the derivative, that's the definition, and then we can multiply both sides by dx. Now, when you look at this little triangle here, do y'all see, I'm gonna zoom way in here. Do y'all see that that triangle is actually like kind of at the top of this little rectangle? Like it's up here. Do you see our triangles right there?
Mhm.
Okay, so in actuality, we know we know the width of this triangle. How wide is this triangle then?
dx.
dx, right? Okay, so this is dx. All right, we know that. Okay, now the height of it, if dx represents the infinitesimal little change we have in x, then the up and down should be the infinitesimal change we have in y. Do you all agree? If this is dx, then this is dy. So this is dy, right? But what's dy? We just said dy is f prime of x dx, right? We have two sides of a right triangle. You can solve for the hypotenuse, right? A squared plus b squared is c squared. So let's just call the hypotenuse h. Do you agree that dx squared plus dy squared, which is f prime of x dx squared, should be equal to the hypotenuse squared?
Yes.
Okay. So now let's take the square root on both sides. The square root of dx squared plus f prime of x times dx squared should be equal to the hypotenuse, right? Actually, I should have called it L, because didn't I say it was L earlier?
Mhm.
These are the same thing. Oh, well, we'll stick with H, okay? Now, check this out. The square root, or maybe I should say this first. Do you agree that at this moment we have a formula for that hypotenuse? And that
Yes.
we can just use the integral to add them up? Yeah?
Mhm.
So right now, here's what I could say. The integral from A to B of whatever it is I'm adding up. And all what I'm adding up is this stuff, right? This. I could put that right here, right now. And that would give me the length of the whole curve. The problem is it's missing something that has been present in every single one of our integrals that we've ever done. We're missing that like dy or dx out there, right? Notice in all the other formulas that we did, when we were doing these cross sections, when we were doing these cross section problems, we had a dx in our formulas, right? Where the heck did it go? Oh, yeah. See, in this formula here, we had a dx. Where did the dx come from? The formula for the volume of that little slice. Where did the dx come from here? Oh, it was the thickness of this little semicircle, right? It was how thick it was.
Mhm.
In everything, when we were revolving things around the axes, right? When we were doing all this, right? All this stuff with washers and shells, washers and shells. The dx always came from the geometrical picture, right? Like we had a picture, and from the picture there was always a dx somewhere in the picture, and it wound up being in our formula, right? So we always just slid it to the outside, and then everything looked natural, and this one doesn't. Do y'all see that? We don't have a dx just sitting here, but we do. Okay, so I need to do a little more algebra first.
So Professor, is it okay or is it legal just to cancel the square with the square root?
No, because it's addition between them. If it was multiplication, you can do it, but it's addition.
Okay.
It's
What
kind
if
of
we
like,
separate them?
no, you can't. Think about that problem right there. That's the square root of 15, right? Or 13, sorry. But if you split them, square root of 9 plus square root of 4, well, then that's 3 plus 2, but that's definitely not that. So this is a violation. Now, if you change that to multiplication, then it works. Because 9 times 4 is 36. Square root of 36 would be 6. But so is 3 times 2. 3 times 2 would be 6. So we can't. Now, we can do something, though. we can notice that if you just take the dx, square it now on the second one, on this right here, we can square both the f prime and the dx. So I can take the f prime of x, I can square, let me put in brackets just because that's what most books do, square it, and then I can say times the dx squared. That should be what h is. And do you see now that they both have dx squared?
We can do a u substitution.
No, we're not integrating, just algebra. Pull a dx squared out of them, right? 1 plus f prime x squared. So they both have dx squared, so I factor out a dx squared. Do y'all agree that this is what we would get?
Mhm.
Okay, and now you can, because there's multiplication between them, you can take the square root of each one individually. And what would be the square root of dx squared?
Dx.
Dx.
That's dx. And then the other one, you can't get around it. You just have to take the square root of it. So
This looks quite like trigonometric integral.
trig sub, yeah, a little bit. It does look a little bit like it. It's not though. This is a formula for finding the length of a curve. All right,
So right now we're only driving the formula.
that's right. So here's where we are. We were sitting up here, we're like, this is weird because we don't have a dx or dy out here. Well, now we do. So this now becomes integral a to b square root of 1 plus the derivative of the function squared dx. And that, my friends, is, I'm going to call you friends even if you don't consider me a friend. That's the formula for the length of the arc. That's the formula. Beautiful. So if somebody gives us a function and they want us to calculate the length of the curve, then what we're going to need to be able to do is take the derivative of that function, square it, add 1 to it, take the square root of it, and pray that we can integrate it. Because this integral might turn out to be not good. It might not. And so in all seriousness here, like, it is very tough to calculate arc lengths, because a lot of times if you just if someone right now just throws a function at me, I would be willing to bet 98%, 99% that I wouldn't be able to find you the arc length, not without a computer. And that's because so many things have to work out perfectly for this formula to work. But it
Well,
is
I
a
think,
formula.
isn't the problem that first we need to know some of this stuff to be able to solve it? Because if we just throw numbers or letters or whatever, we won't be able to, it will not be solvable, right?
Why don't we do an example and I'll show you. I'll show you. Do you want me to give you an example that works first, or do you want to just someone throw me a function and I see if I can do it?
One that works.
Oh, I was gonna throw a random function at you.
What do you want, Cameron?
Just
Cameron,
a random, just like a random quadratic.
Okay, let's try it. Let's try a random. What quadratic do you want? Don't go crazy on me. Let me just give
Okay,
me a random.
Okay, something simple. X squared minus 2x plus 1.
Okay, here we go. So x squared minus 2x plus 1. Now you have to give me an interval. So why don't we take a quick look at it? I'm sure you all know what this function looks like, but we'll just graph it. I know you can't see it yet. Minus 2x plus 1. Here it comes. So there's the function right there. Can you give me an interval so I can try and see how long it is? Anything you want.
Okay, -1 to 3.
Okay, -1 less than or equal to x, less than or equal to 3. So that's it. That's -1 to 3. That's the curve. You want me to tell you how long that is, right? If you were to take it off the page and stretch it out, give me the length. All right. Here I go. So the length should be equal to the integral, wait, what was the interval again?
Negative 1 to 3.
Negative 1 to 3. I need to put that here. So my integral is going to go from negative 1 to 3. And then it's going to be the square root of 1 plus. Now I need to go do some work on the side, because what goes in there? The formula says I need to take the derivative, stick it in there and square it, right? So I'm going to take the derivative of that function. The derivative of that function is
2x minus 2.
2x minus 2, okay? Now I need to square it. So if I take that derivative and I square it,
4x squared minus 8x plus 4.
yeah, so I'm going to take it and square it and get 4x squared minus 8x plus 4. And that's what I have to stick in there, right? So that's going to be plus 4x squared minus 8x plus 4. And then don't forget dx on the outside. All right, let me clean that up. That's the integral from negative 1 to 3 of the square root of, all I have to do is add that 1. So
And also
4x
you have to square it, right?
I'm sorry.
Oh, you already squared it. I'm sorry.
Yeah, I squared it already. Yep.
Yeah.
And actually, you know what, Cameron? I might be able to do that. I'm going to complete the square and do a trig sub, right? Because I have a quadratic under a root. So if I complete the square and do trig sub, I think I can get it. All right, should I continue? Yeah, okay, so real quick completing of the square over here. So I take half of 8. Oh wait, no, I need a 1 out front. Oops. So I'm going to pull the 4 out. And then I have x squared minus 2x plus 5/8. And then I'm going to take half of the 2, which is 1, or negative 2, which is 1, then add and square it and add and subtract. So you wind up
Wouldn't
getting
it-
x minus 1 squared. Go ahead.
Wouldn't it be 5/4? Because you took a 4 out.
Yeah, I don't know why I put 8. Thank you. 5/4. Thank you, Minato. Okay, so I took half of that and squared it, add and subtract. So I added 1, subtract 1. When I subtract 1 from that, I should get 1/4. Everyone understand what I did there? I mean, okay. And then that's what's going to go underneath that root, right? So when I put that under the root, the 4 can come out. So I'm actually going to have a 1/2 out here now because the 4 came out on the bottom. Integral negative 1 to 3 square root of x minus 1, oops, x minus 1 squared plus 1/4 dx.
Wait, how did you get to the 1/2 again?
This, okay, so everything here is going to wind up going under a square root, right?
Mm-hmm.
Oh, wait, I don't know what.
It's just 2.
Friday. Yesterday, I thought it was Friday. All day, I thought it was Friday. And then today, I don't know what I think it is.
It's time for you to take a break.
It is. And tomorrow is what's called Employee Development Day,
Ugh.
which means all day long I have to go to Zoom meetings from like 8 a.m. to like 4 p.m. I'm not happy. All right, it is what it is. Let's keep going. All right, so so now what I would do is try and integrate that. So I'm going to do that on the side here. I'm going to make a quick u substitution. U is just going to be x minus 1. And that means du is dx. And that just allows me to rewrite this integral as the square root of u squared plus 1/4. And there's no constant I have to take out. Everything's beautiful. Now I do a trig sub. And what's my trig sub? U is,
Sine.
it's a plus though.
Tan.
Oh,
Plus.
10.
Tan, what's a?
Secant.
1/2.
1/2, right? So 1/2 tan theta is our trig sub.
Oh.
D is 1/2 secant squared theta d theta. And the square root stuff all turns into 1/2 tan, no, secant theta.
Secant theta.
All right, so that means this integral becomes, the whole square root thing is 1/2 secant theta. And then the du is 1/2 secant squared theta d theta, which is 1/4. Hey, I didn't make up this problem. This is Cameron's fault. But it's a good problem. I like this. So secant times secant squared, secant cubed, but you know what? Secant is 1 over cosine. So, oh no, we did this problem, didn't we? We've done secant cubed. We did that in class.
I think it was on the test.
Secant cubed. We did this by doing integration by parts. We do secant squared here, we do secant here, and then we go and down. I'm not going to go through that. That's a long problem. Okay, but maybe I'll go back and look. When did we do it? This would have been a long time ago. This would have been in September. See if I can't find it. Oh, maybe it is my day. Okay, so here's secant cubed, right? Okay, so secant cubed, we tried a bunch of stuff, didn't work. We finally got the integration by parts right here. We did secant squared goes to tangent, and then we came down here, and then, oh, it appeared on the other side. We had to add it to the other side. Oh man, what a mess. But there it is. So I'm going to cheat and copy that. Hey, this is a 1%er problem. It looks like I'm gonna be able to do it. So I've got that in there. So I have a 1/4 out front. So this is gonna become 1/8 secant x tangent x plus 1/8 natural log of secant x. Wait, it's secant. Hold on. Why was it secant? It should be secant theta. Hold on. It should be secant theta for us.
Yeah.
It's theta. Secant theta tangent. The original problem I gave y'all was x, secant cubed x. We hadn't done trig sub yet. Secant theta plus tangent theta, absolute value plus c. All right, there it is. There's the antiderivative. Paste. Now I put it here. Now there was a, I need to replace all my thetas with what? So I've got to make a reference triangle. Jeez. Here's theta. I know tangent theta is, so using this right here, tangent theta should be 2u over 1. This should be square root of 1 plus 4u squared. I just multiply both sides of this by 2. And so tangent theta is 2u over 1. So there's my tan theta. And there's this part. And I really don't want to continue this problem. Because then I still have to
That's
plug in
fine.
-1, you know?
You proved the point, Professor. I don't think
We can do it. Okay, we can do this one, but we got kind of lucky. Like Cameron, if we put in like x cubed, I think I'm done. You know, like if you put x cubed here, because my derivative then would have an x squared, and then when I FOIL it out, I'll have an x to the 4th. And when I put an x to the 4th under here, it ain't happening because I can't complete the square.
Mhm.
So we have to be extremely careful, all right? I think because we did spend some time on that, let's at least find out what the answer is. So let's do the integral from, what was it, -1 to 3 of the square root of 1. Wait, what was it when we added? It was 4x squared. No, was it 4x squared? No.
1 plus 4x squared minus 8x plus 4. So
It's 8x plus 4. So it became +5, right? Before we completed the square?
yes,
Dx. Boom. 9.29. 9.2935.
So hypothetically, if you put in 4x to the power 4 right now, the computer will be able to tell us the answer.
Oh yeah, the computer's gonna be able to handle it.
Oh, okay.
Now you might be like, well, why are we doing all this then, right? The computer can handle it. Look, that was like an instant, right? Well, you have to understand how the computer just did that. It's using series. It's using what are called power series. And so that's chapter 8. That's what we're going to get into, is series. And what we learn in that chapter is that, you know, all the algorithms that these computers use are based upon series. So you have to understand series to know how a computer works. Okay. Yeah. So let's do one that works out nicely. All right.
So I'm checking, we only have like 3 questions from this part 7.4 and 7.5.
Yeah, there's not much. It's just to let you know that we have a way of doing it.
Okay.
Yeah, it's yeah. So let's do y equals 1/3 x cubed plus 1/4x on the interval 1, 2. All right, so this problem had to be very special, you know, had to be very, we had to be very careful when we made the problem so that it would work, okay? So let's go through this. We want the length of the curve, of this curve on that interval. So we have the formula, we know what it is. We know we're gonna need the derivative. So I'm gonna call it y prime instead of f prime of x, call it y prime. Derivative of this is just gonna be x squared minus You all okay with that? We're taking the derivative of this, which is the same as 1/4 x to the -1. So the -1 comes out, you subtract 1, becomes -1/4 x to -2. All right. So that's your derivative. And now I need to square it. So when I square this, that means I need to square this. Which means we have to FOIL. So x to the 4th, and then here to here. What happens there on the second multiplication?
X to the 0.
Which is 1.
So it would just be 1/4 minus 1/4.
Minus 1/4, right? The x's basically go away. Same with the inner one. So we get a minus 1/4 there. And then we did last one, we get a plus 1/16 x to the -2. Let's clean up a little bit. Minus 1/4 minus 1/4 is minus 1/2.
Is that so that x to the -2, would that,
Be -4.
Yeah,
wouldn't it be -4?
yeah, this is one of those days. I have too many of those. I just hope I don't become that old professor who just makes all these stupid mistakes, you know? I've been in that class. Don't like it. I don't think I'm there yet. I'm hoping I'll recognize it when it happens. Or that, you know, that they get lost, you know, they're sitting there and they get lost in their own work. Oh man, there's nothing more.
Well, even if that happens, you'll be able to tell that people are actually paying attention.
Yeah, that's true. But I didn't do it. I didn't do it for that reason. I messed up. Okay. All right. So now let's think about the formula. The formula is the integral from a to b. Here they give us 1 to 2 square root of 1 plus that, right? 1 plus this thing. So I'm going to go ahead and add the 1 to the half right now to save myself a little time. So one take away a half is going to be a positive half. Then I have x to the 4th. Then I have plus 1/16 x to the -4 dx. Now, when you look at that, you might be like, yeah, right. We're supposed to be able to get that, right? Like that looks really bad. That looks really, really bad. But it's not. It's not bad at all. Watch.
So what was the move that you made before that integral?
Remember, the formula has square root of 1 plus the derivative of the function squared, right?
Uh-huh.
So what I did is I went ahead and took that 1 right there and I added it to this, and that gave me the positive 1/2.
Okay.
I just didn't feel like writing 1 plus all that and then having to rewrite the whole thing again. Okay, so watch what I do here. That's the square root of 1 over 2 plus x to the 4th plus 1 over 16x to the 4th dx. So we are going to put all of this into one fraction by getting a common denominator. We're going to put all three terms together. So that's an x to the 4th over 1. So that means I have to multiply.
How did you make the 1/2 positive?
That's what I'm saying. In the formula, it's the derivative of the function squared, right? Which is what I have in this box. But then plus 1. So let me just write it down. Let me write it down. The step that goes right in here is integral 1 to 2 square root of 1 plus x to the 4th minus 1/2 plus 1 over 16 x to the negative 4 dx, right?
Mhm.
Now, what happens when you put 1, take away 1/2?
Okay.
Okay. So I just skipped this step. So rewriting every term as a fraction, let's get a common denominator. My common denominator will be 16x to the 4th. 16x to the 4th, right? So I have to multiply, let's see, this one by 8x to the 4th on the bottom, 8x to the 4th on top. What about the next one?
16x to the 4th.
X to the 4th, and then 16x to the 4th. And then the last one, I don't need to do anything. So now that they all have the same denominators, the new numerator is going to be 8x to the 4th plus 16x to the 8th plus 1 over 16x to the 4th dx. And that becomes 16x to the 8th plus 8x to the 4th plus 1. I'm just putting in descending order on the top. And now this numerator factors. It's like a quadratic. It looks kind of like a quadratic. Can somebody tell me what that is? It's a perfect square, by the way. It's something times itself.
Four
4x to the 4th power.
4 power plus 1.
1. That's it. 4x to the 4th plus 1. So if you FOIL this with itself, you will get back the top. See what I'm saying? Like they had to make this problem where it would work algebraically. Like this all had to happen for this to work.
Yes.
So now what we have is this integral from 1 to 2. We have on the top, we have, well, I can do it. We have this 4x to the 4th plus 1 squared over 16x to the 4th dx. And now because it's a square root, I can do the square root top and bottom separately. And when I take the square root on top, it just gives me the 4x to the 4th plus 1. And when I take the square root of the bottom, I just get 4x squared. And I no longer have a root. We're almost there. Split this into 2. So there I just did 4x squared, I'm sorry, 4x to the 4th over 4x squared. That's just x squared. And then 1 over this, which is just that. And now we can find the antiderivative, power rule, right?
The stars had to literally align for that problem.
Exactly. Yeah, that's why these problems are just meh. You know, they have to work out perfect. So there's not a whole lot of examples that we can give you because they have to work out perfect.
So whenever they make these, do they make them actually knowing the final answer and working up the other way, backwards?
They make something that they know what the integrand is going to do, and then kind of reverse engineer it. Yes. Okay. So I have a more profound question now. All right. I've given you the formula. You get the idea. I think you just have to take the derivative, square it, throw it in there underneath the square root, add 1 to it, and hope, right? Hope that you can then do the algebra. So let's take something that we've done already. Like, well, we've kind of addressed this problem several times. This whole concept kind of forced you to continue to think about this. Let's say we have a circle, right? We proved already in this class, we proved that the area of a circle is pi r squared. And if you go back and look in your notes, to do that, we had to use trigonometric substitution. And then the other day, I proved that the volume of a sphere is 4/3 pi r cubed. And that we proved by taking the circle and wrapping it around the x-axis, right? So guess what I'm going to ask now? For us to prove what?
Pi.
What?
Pi r,
I
2
know.
pi r,
Oh, just pi.
What's the circumference of a circle?
2 pi r.
2 pi r. Prove it. Right? Prove it. Well, isn't the circumference of a circle just, you know, all the way around, right? So why don't we see if we can't figure out what the distance around half of it is?
Pi r.
Because if we look at just half of it, we look at just the top half is a function. And we know the equation of that function. It's y equals the square root of r squared minus x squared. How do we know that? Because I've done that 3 times now. This is the 3rd time. Remember, I just start with the equation x squared plus y squared equals r squared, and I solve for y. Okay, so we know that the equation of this circle is that. And now we need the arc length, right? And we will go from negative r to r, right? Because, well, we could just go the first. Y'all want us to go from 0 to r and just multiply that answer times 4? Or do you want to go from negative r to r and double the answer? I'm going to go 0. I don't like negative r. So I'm going to see if we can do this. Can we find the arc length of the orange one? And then if we can, multiply that answer times 4 and hope we get 2 pi r. You ready to do it? I'm not. Because we have to use the formula, which means we have to take derivative of that, right? And then square it, and then add 1, and then take the square root of it and hope we can integrate it. All right, it is what it is. Here's a derivative. So we're taking derivative of this. Remember that r is a constant. So the derivative of the square root of something is 1 over 2 times the square root of that something times the derivative of what's inside of it, which is negative 2x. Right? That's our derivative. Let's clean it up. Is everybody in agreement on that? We all happy with that derivative? Square it now. X squared on top, bottom. Ooh. Ooh. Ooh, that square root went away. I like it. I squared the negative x, so it became positive x squared, right? I don't know, maybe this isn't as bad as it looks. So we're going to go to the formula for arc length, integral a to b square root of 1 plus, by the way, you can put y prime squared here instead of x prime or f prime of x, because y prime and f prime are the same thing. So the formula could also be rewritten this way. All right, I'm ready to roll. Are y'all ready? Let's do this. So we are going to go integral where to where?
0 to r.
0 to r. Let's go ahead and throw the 4 out here in front right now, because that'll be our total circumference, right? Just put it out there now. Then I have square root of 1 plus, and then this thing that we just found, x squared over r squared minus x dx. All right, now when you look at that, again, you might look at it and just not be happy about it. But whenever it looks like something bad like this, at least just try and put them together, like get a common denominator. So try and put these two together. So that means I need to look at that as 1 over 1, right? This is 1 over 1. So I have to multiply the whole top by the denominator and the whole bottom by the denominator. 4 integral 0 to r square root of, okay, what does the top become? If I take that and I add this,
R square.
just r squared. Oh man, life is looking pretty good. Over
R square minus x square.
Yeah.
And it's just 1 over negative x square.
Pardon me?
Can we, oh, we can't separate it, right?
We have, at this point, we can take the square root of the top and bottom separately. Can't we?
Okay. Yeah.
And the square root of the top is just r, isn't it?
Mm-hmm.
And if it's r and r is a constant, it can come out. So I'm going to pull the r out. And I have a 1 left on top. On the bottom, I have this.
Can't we just take the square root of r? Oh, because there's a negative sign in between.
That's right. We can't do them. But we could use trig sub, couldn't we?
Mm-hmm.
But even better than trig sub is formulas. This is formula 16. 1 over, we have, instead of a squared, we have r squared. So this is r squared minus u squared. For us, u is x. So it should just be arc sine of u over a.
So can you use?
Trig sub would take us to the same place. What's that?
So yeah, my question was, if I don't do trig sub, instead just use formulas like these.
Yeah. For this one, we could, because it's exactly that form, right? It's exactly that. So we can use the formula. So where am I going? So a here, this is the a, and this is the u. So according to the formula, this is 4r times arc sine of u, which for us is x, over r, a, which for us is r. We want to evaluate that from 0 to r. So don't forget, this is a definite integral, right? So we find the antiderivative, and then we have our limits of integration, and then we have the 4r that's going to come along for the ride. And now, man, we are there. We just have to plug in.
So even if we force the denominator under the square root, we won't be able to use the formula.
Even if we force the what?
So like, for example, if we never had this and we remember how we used to force using complete the square or like u substitution to make them look like a trig sub problem. So if we do that and get it terms of the same, can I use the formula then?
Yes, you could.
Okay.
But if you go back and look at your test, on all your tests, I always threw something else out here, like an x squared or an x cubed or something like that, so that you couldn't use the formula.
Oh, okay.
Yeah, because then it would just be a trivial exam, because you would just you complete the square, you get it, and you go right to the formula. So you can basically not have to do trig sub. All right, so I'm plugging in R first for X, so I get R over R. And then over here, I plug in 0. So 0 over R is just 0. And we're there. R over R is 1. So let's start with the one on the right. Arc sine of 0 is saying, what angle do you plug in on the unit circle to get a y coordinate of 0? What angle?
0.
Pi.
0.
Oh, 0. Yeah.
So that whole thing is 0. So mine is 0. And then now this is saying, where on the unit circle is your y coordinate 1?
Pi.
Pi.
Pi over 2.
Pi.
Pi over 2.
45.
Pi over
Pi
2
over
and
2.
3 pi over 2.
Pi over 2. So that's pi over 2. And so your answer is 2 pi r. All right. So we have proven the circumference of a circle is 2 pi r, the area of the circle is pi r squared, and the volume of a sphere of radius r is 4/3 pi r cubed. And we've used integration to do all of them. Pretty awesome. All right, moving on. Next topic. Ready? 7.5. Surface area. So this is a separate concept, all right? We're not talking about arc length anymore. We're talking about surface area. So let's say that we take a curve, started at some point A, ended at some point B. So many things we can do with this, right? Find an area, we can wrap it, we can find the length of the arc. There's all these things, but what we're going to do now is we're going to rotate this around the x-axis. Okay, so just like we had done in 7.2, we're going to wrap this thing around the x-axis. When we wrap that around the x-axis, we know that we get this three-dimensional solid, right? We know how to find the volume of that, don't we? What we don't know yet is how to find the surface area of it. So instead of looking at that as like a solid, I want you to just think about the outer edge of it like a shell. So we're talking about, just the outside of this all the way around. The question is, what's the surface area? So it's kind of like if you wanted to paint that solid, right? If you had a solid, if you wanted to paint the outside of it, what would the surface area of it be? That seem reasonable? Yes? Yeah.
Mhm.
Okay. So here's how we're going to do it. We need to find a formula that we can use an integral on and add them all up. So imagine again that we kind of zoom in here. Zoom in here. What I'm going to do is try and convince you that if we were to take just a little piece of this, right, just a little piece of that, and wrap just that little piece around the x-axis. If we wrap that around the x-axis, we would get this rubber band. Do y'all see that? See, I'm not taking a rectangle and wrapping the rectangle. I'm just wrapping that outer edge around. And if I do that, I get this rubber band looking thing. Do y'all agree?
Mhm.
Okay, so let's take that rubber band, see if we can find a formula for the area of that rubber band. So what I'm going to do is I'm going to cut it. I'm going to take my scissors to this rubber band, and I'm going to lay this rubber band out. Like this. I'm going to try and figure out what its area is. So I'll start with this. Do you know how long it is?
Top of the function.
Remember, it got wrapped around, right? So isn't this very similar to when we were doing the shell method? When we opened up that shell and we wanted to know how long the shell was, wasn't it just the circumference of this thing? Well, for us, the radius of this rubber band goes from here to here. That radius is actually just the height of the function. That's just the distance from here to here. That's f. Does that make sense?
What is the diameter then?
Well, the diameter would be half, but we're looking for the circumference of this. The circumference of this rubber band is 2 pi r, right? It's 2 pi times the radius, but the radius is the height of the function. So that's f of x. So you'll see that? You wrap this around, you get a rubber band. When you cut the rubber band and lay it open, the length of the rubber band is the same as the circumference, which is 2 pi times the radius, but the radius is the distance from the axis of rotation to the rubber band's edge. So that's the function. The only other thing I need to find the area is this. Slow down. It's not dx. What is it? How long is this little piece?
Is it dy?
X.
Let me zoom in on it. All right, I'm zoomed as far as I can go. So let me zoom in on it a little bit more.
Is that a triangle?
Is it L?
It's L. See what it is that little triangle. I mean, that little right triangle in there. That length is the arc length. That's how long it is. It's the arc length on that little piece. But we already came up with the formula for the arc length. It's this. So guess what? To do a surface area, your formula is going to look almost exactly like your arc length area with one exception. We have to throw this into it. Because this length or this times this gives us that area and we want to add them all up. If you're not following where the formula comes from, it's okay. Just take the formula. So the surface area would be integral a to b. Now, I have 2 pi times f of x. That's this piece right here. The 2 pi can come out. F of x has to stay in. Times the little arc length of the rubber band, which is this. And that's your formula for surface area.
And is that like integration by parts?
Well, it'll always depend on the function. The function will always dictate what this turns into. So by comparison, the arc length that we just found in the previous section was this integral. Right? So what's the difference between the two? That's it. That's the only difference between those two formulas. This gives you arc length. If you multiply by the function, multiply by the original function and 2 pi, then you will get the surface area.
So are we supposed to expect anything like this on the exam?
Yeah, of course. Yeah, you have a few homework problems with it. So I'll let you mess with that. All right, so guess what I want to show you now? Check, check, check. The area of a circle is pi r squared. The volume of a sphere is 4/3 pi r cubed. The circumference of a circle is 2 pi r. How do you think I can use this new information here?
The surface area of it.
Surface area of a sphere, right? So the volume and the surface area, we're talking about a sphere, right? So that's the volume of that solid ball. But what's the surface area of a ball? Well, we could look up the formula, couldn't we? We could. Let's not. Let's just come up with it on our own. It's exciting. So here's what we got. We know that we have this first quadrant part of the circle. We're going to wrap it around the x-axis, right? And find its surface area. So this is the curve y equals square root of r squared minus x squared. We've already done the derivative, haven't we? We did the derivative earlier, check, and we squared it. What was it when we squared it? It was x squared over r squared minus x squared. Trying to save us some time, yes? Just look at the previous, when I showed circumference.
Yeah, that's right.
Yeah, not only that, I mean, look, if you go back and do all the work, right? Where was the problem we did? Right here. This integral right here turned into this, right? Actually, we did the 1 plus, didn't we? And we got a common denominator. And then we took the square root. So isn't this what we should get right there? With an r outside? I don't want to go through all this work again. So let's do this. I'm going to set up the integral. Hopefully you're following. I'm going to put a 2 in front of the integral. The reason I'm putting a 2, not a 4, is because I'm going to wrap this around the x-axis, which is going to give me just half of this sphere, and I need to double that answer. So I'm put a 2 out there for that. But then I'm also going to put a 2 pi out here. Why am I going to put a 2 pi?
The surface area.
Yeah, it's part of the surface area formula, right? I'm also going to put an r out here. Why am I going to put an r? Because when we did the 1 plus the derivative squared, right? When we did all that on the previous example, we know that we got right here. This was it, 1 plus all that derivative squared, and then we did the square root top and bottom. We pulled this r out, and it was a 1 over this. So let me throw that in there. So I know I'm going to have a 1 over r squared minus x squared dx. But what's going to be sitting in front of this? What's in front here that I have not accounted for? That's different in the surface area.
F of x.
Square root of r squared minus x squared.
Right. The formula has the 2 pi array accounted for that. This has all been accounted for. I still need this, which is the original function. So I just need to put square root of r squared minus x squared. Wait a minute, hold on. This denominator was not this, wasn't it this? I forgot to put the square root on that, right? Right there, forgot to put the square root. Go back and look at the work. Right here, it was a square root of that. Oh my goodness, do y'all see what happens?
It's just one.
They cancel?
I cancel.
It's beautiful.
Oops. Doom, doom. Doesn't that mean we have 4 pi r integral 0 to r of just 1 dx? Now, integrals don't get any easier than that. That's just 4 pi r, antiderivative of 1 is just x, and we evaluate from 0 to r. So when we plug in r, we get 4 pi r squared. And when we plug in 0, we get 0. So the surface area of a sphere should be 4 pi r squared.
This is crazy.
Crazy. It's crazy. But it's true. 4 pi r squared. There you go, the area of a sphere. 4/3 pi r cubed. Volume, right? Area. We've proven all these. It's pretty cool, in my opinion. All right, we've got about 15 minutes. I have one more thing to show you. And then we are going to be done with chapter 7. Now there's some applications, but I tell you what, because we're a little bit behind, 7.6, I don't even have it in here, but today is the, what, 29th, we're supposed to be here. So we're so far behind already. We're just going to just go right into chapter 8 next class. All right. So make sure you get through the 7.4 and 7.5 homework. But there's one last problem I want to show you. And this is known as the paradox of Gabriel's horn. I think that's the way you spell Gabriel, is it? Is it E-I-L?
That's right.
Just like that.
Yeah, it's like that. The paradox of Gabriel's horn. All right, so here's the idea. It's a paradox, which means at the end of this, we're going to be scratching our heads. Let's say that we take the function f of x equals 1 over x. Okay. And let's look at it on this interval 1 to, I don't know, let's go to infinity. So this graph looks like this. One goes in, 1 comes out, and then it just kind of tapers down and heads towards the x-axis like that. It goes forever, right? Goes forever. Now, imagine that you wrap this around the x-axis. Okay, we haven't talked about doing anything like that before. But if you wrap it around your x-axis, you're going to get a funnel that gets smaller and smaller, but goes forever and ever, right? And the question is first, what is the volume of that solid? All right, well, this should not be too bad because we have vertical rectangles. Our axis of rotation is the x-axis. So we just use washers, right? Washers, right? We have a top function. Top function is 1 over x. Bottom function is just 0. So this should go pretty clean, right? It should be the integral from 1 to infinity. We're using washers, so I should have what out front of the integral?
Pi.
Pi. And then it should be my outer radius squared. What's my outer radius? Distance from the axis of rotation to the outer edge.
It's just f of x.
Which is just f of x. So it's just 1 over x. That's my outer radius squared, right? Minus the inner radius, which is just 0 squared dx. And that's just integral 1 to infinity of 1 over x squared dx. And does anybody remember what that integral is? What? I just went right to it. Oh my gosh, I did not plan this. We proved this in class. We did integral from 1 to infinity of 1 over x to the p. It will, if p is greater than 1, it's going to converge to 1 over p minus 1. And if it is less than 1, it will diverge. So it should go to, this should go to what? It's going to converge to, well, we have a pi out front, but then 1 over p minus 1, right? Isn't that what it was? 1 over p minus 1. So 1 over p for us is 2. I guess I should have pointed that out. P is 2. I thought that was obvious. 1 over 2 minus 1. So this just converges to pi. So that means what? This infinite funnel, right? This infinite horn, this funnel that goes forever. If you could like imagine turning it upright and starting to pour liquid into it, you could fill it up, right? The volume of that would be pi, and you would fill it. Okay? That's not the paradox, though. That's the calculation, okay? The volume of that solid is pi, converging to pi. Now, what about the surface area? The surface area. So what's the surface area of this thing? Okay, well, if we're going to do the surface area, we need to be able to do this integral. 2 pi integral a to b. We're going to do the function times the square root of 1 plus the function derivative squared dx. So I need the derivative of the function. Let me do that on the side here. F of x is 1 over x. The derivative of that is negative 1 over x squared. I hope you can all do that, right? I take the derivative, I take that derivative and I square it, which just gives me a 1 over x to the 4th. So here's where we are. 2 pi integral is going to go from 1 to infinity. F of x first. F of x is just 1 over x times the square root of 1 plus what?
1 over x to the 4th.
1 over x to the 4th dx. All right, this integral, I hate to tell you, is not something we can do. All right, it's not, unfortunately.
What about the computer?
Can you not make the 1 x over 4 over x over 4?
Yeah, we can do that. I'll do that just for the algebra. Let's just do it. We can make this 1 over x square root of, it'll become x to the 4th plus 1 over x to the 4th, right, dx. Agreed? And we could even at that point do like the square root of the top and bottom, but at that point you'd get stuck.
You'll get the same thing.
Well, what would happen, I don't want this to be part of our logic here because it's going to just confuse us later, but let's imagine we do the square root of the top, which would just be square root of x to the 4th plus 1 over, let's see, the bottom, we have this x that's there, we have that x, and then the square root of x to the 4th would be x squared dx, like that. So that's really x cubed down here. Is that okay? And that's where you're going to be stuck. Unfortunately, there's nothing we can do there.
Later on, besides this class, is this just out of our reach, or is this out of like maybe an advanced reach too?
No, see, here's the thing. This is probably out of reach for everyone. That's why power series are going to be so important to us. Every function can be converted into its power series. And once you convert it to its power series, then everything becomes easy. But if you don't have power series, you're basically stuck here. There were two men who developed calculus. There was Isaac Newton and there was Leibniz, and they both created calculus on their own independently without knowledge of one another. And that's why we have like two notations in calculus. We have Leibniz notation, dy dx, and we have like more of Newton's, which is more like the F prime stuff. It turns out though that even though they both developed calculus, Newton was the one who had power series. Like he figured out power series, and Leibniz didn't have power series. So when people compare, I'm a fan of Newton because you realize later, like, wow, without power series, you are really kind of stuck still. You're really treading water when it comes to things like this. So look, we'll go to Wolfram Alpha, and we'll type it in, and we'll see what happens. Wolfram Alpha. Let's try to integrate. This will tell us whether or not it's really out of reach. Integrate the square root of x to the 4th plus 1. Oops, 4th plus 1. All of that over x cubed. Let's just do that part of it and just see what it does. If we see anything like Earth, oh, you know what? Okay, all right, it can be done. It's nothing that we've ever done. We haven't done anything involving inverse hyperbolic trig functions. But so it could probably be done by hand, but it's not anything that we have messed with. But it's okay that we can't do this because of what I'm about to show you, all right? I just want to know something about this. And I want you to focus all of your attention right now on this expression. Forget that it's inside of an integral. Forget that that's in an integral. Tell me if you think that if you believe me when I tell you that this is true. Yes or no? Do you agree with that?
Yes.
Yes?
Yes.
So what you have to convince yourself of is that numerator is bigger than that denominator, right?
Yes.
So x to the fourth plus 1 is definitely bigger than x to the fourth. So when you take that and divide it by that, everything that's underneath that root is definitely bigger than 1.
Yes.
And the square root of something that's bigger than 1 is still bigger than 1.
Yes.
So if we're multiplying 1 over x by a number that's bigger than 1, then that's definitely bigger than 1 over x by itself, right?
Yes.
Okay. Now, why am I showing you this? Well, if what's in that integral, I mean, if what's in here in red, right? If that right there is bigger than x, then that means that that integral should be bigger than 2 pi integral 1 to infinity of 1 over x dx. So what I'm doing is I'm saying that integrand is bigger than that integrand. So this, if I add all these up, it should definitely be smaller than adding all these up. Make sense?
Yes.
But what does this integral do?
It's just not a natural log.
Yes. But this goes back to this. This is 1 over x to the p. Here for us, p is what?
1
1. What happens if p is 1?
diverges.
Diverges. In fact, what we're saying here, and if you go back and look at the work we did for this integral, you'll see that this integral right here, that actually went to infinity. And so we have 2 pi times infinity. And the integral we're interested in is bigger than that, which means that it must be infinite. This is called a comparison, all right? We're taking an integral we can't do easily and we're comparing it to an integral we know something about. And so the conclusion here is this. Gabriel's horn has a volume of pi, but a surface area that's infinite.
That doesn't make sense.
But isn't pi kind of infinite because it just goes on forever?
It is, you can't say it's infinite. The decimal expansion of pi is an infinite decimal, but pi is bounded. I can pick a number bigger than pi and pi will never get there, like 4, right? If I give you the number 4 is always bigger than pi. So the number pi is bounded. To be infinite means you're unbounded. So there's the big distinction between the idea of being unbounded versus repeating decimal. I mean, I guess an easier example of that would be like 0.33 repeated. That's just 1/3, right? It just goes forever. But the fact that the decimal goes forever doesn't mean that the number itself is infinite. 1/3 is just 1/3. So the paradox, again, is that you have this horn that you can fill it with a finite amount of stuff, right? Like I could fill it with paint and I could pour in exactly pi and I'd fill the horn, but it's impossible to paint its surface. You don't have enough paint to paint the surface.
But I mean, is that even possible?
Well, the paradox is in the idea of what we mean by area. Because when you talk about area, right? When you talk about area, when you go and let's say you're looking at a wall and you're like, oh, what's the surface area, right? You are measuring length times width. It's 2-dimensional, right?
Mm-hmm.
But if we start talking about paint, right? How much paint it takes to cover a wall, that paint has thickness. So it's actually not 2-dimensional, it's 3-dimensional, right? So this is it's kind of using the fact that, you know how like a line doesn't have any thickness to it?
Mm-hmm.
Right? Take 2 points, you draw a line between them, you say, how thick is that line? Well, lines have no thickness. when you talk about surface area, you're talking about two-dimensional. There is no third dimension in an area measurement. So what's the paradox is created by the idea of what paint is, right? So I'm saying I can pour paint in here and fill it, right? It's a volume, but I can't paint the surface because I don't have enough paint. And it's
So
because
maybe-
you're looking at paint as being, you're looking at paint as being two-dimensional when it's actually three-dimensional, because right when you paint a wall and you run out of paint, you run out of paint because you have a finite volume, right? It is a volume of paint. You're putting it on a two-dimensional surface, but it's going on three-dimensionally. There's thickness to that paint.
Oh, I see what
So
you're
you're
saying.
painting, and when you paint, right? If you go, too thick with your paint, you're going to go through your paint, right?
Yes.
The reason why we have an infinite surface area here is because our paint has no thickness. It's a zero
Understood.
thickness paint. It's weird. It's weird. That's why it's called a paradox.
It basically depends upon the brush you use to paint it.
Yeah.
What if you think about it like in the realm of chemistry and physics? Because I mean, yeah, eventually, yeah, the horn's gonna get small enough to where it's about the size of an atom.
Okay, so that you brought up a very good point.
But then at that point, yeah, then it would get stuck and stop flowing through it.
Exactly. However, mathematicians don't think about it that way. Because in math, we can cut things as small as we want. We never run out of anything. So, if you tell me that you have an atom, right? And you cut it, you're telling me that at some point you can't go any smaller. Mathematicians can always go smaller because you tell me
Cool.
how small is the smallest and we just go half of that. So what I'm getting at is there is a disconnect. In the real physical world, the math doesn't line up exactly with the reality, right? And math is always just used as a tool to try and model what's happening in the real world. But a pure mathematician understands that this problem here has nothing to do with physics. It has nothing to do with the smallest particle or anything like that. This is based on the assumption that you can cut anything as small as you ever want to cut it. It's basically saying, it's relying on the idea that between 0 and 1, there's an infinite number of numbers. We've had this talk before. And that there is no number closest to 0. Like there is no number that's right next to 0. Because if you give me that number, you say, there it is, Robert, it's X. That is the number right next to 0. I will always be able to find one closer. All I
Or
have to do
divided
is
or
take that
divided by 2.
divided by 2. And now that's the new X. So you say, well, that one's the smallest. And we say, oh, we'll just divide that by 2. And we do that forever and ever and ever and ever and never run out, right? We'll always have a number. Always. In physics, in the real world, there is a point at which you cannot cut anymore. So this paradox is based more upon the pure idea of surface area and volume as opposed to the limitations of physics, because you couldn't even create this horn, right? In the real world, like you couldn't even create this funnel that goes forever, right? All right, well, we're out of time. Try and get through the 7.4 and 7.5 homework, right? There's not a lot of it. So I think you have a good opportunity to enjoy your weekend a little bit. There's only a few problems here. Looking here. Oh, whoa. No. I was looking to see an old test, but we can talk about that next week. All right, any questions?
Nope.
Okay, chapter 8, start next week. The fun will begin. I want you to come in here next week with an open mind, just kind of like, go get rejuvenated this weekend. Come in and get down to business. All right. Have a great day.
Thanks, Professor.
Thank you.
Professor.
Have a good one.